Let's kick things off by exploring what a p-value actually is. In statistics, the p-value is a number that helps us determine the strength of our evidence against a null hypothesis. Think of it as a tool that tells us how likely it is to observe our data, or something more extreme if the null hypothesis were true. This concept is foundational in hypothesis testing and is widely used in scientific research to draw conclusions from data. Understanding the p-value is the first step to making sense of statistical results and interpreting them correctly. Before we dive deeper into p-values, let's clarify the idea of the null hypothesis. In most statistical tests, the null hypothesis is a default assumption that there is no effect or no difference between groups. It acts as a starting point for analysis. When we calculate a p-value, we're essentially asking, if the null hypothesis were true, how likely would it be to get the results we observed? This framework is crucial for understanding what the p-value is actually telling us. Now let's talk about what it means when you get a small p-value. A small p-value, typically less than 0.05, suggests that the observed data would be very unlikely if the null hypothesis were true. In other words, there's strong evidence against the null hypothesis. This often leads researchers to reject the null hypothesis in favor of an alternative explanation. However, it's important to remember that a small p-value doesn't prove the alternative hypothesis. It simply indicates that the data are inconsistent with the null. The flip side, a large p-value, usually greater than 0.05, means that the observed data are quite likely under the null hypothesis. It suggests that there isn't enough evidence to reject the null hypothesis. It's important to note that a large p-value doesn't prove the null hypothesis is true. It simply means we don't have strong evidence against it. This distinction is crucial for proper interpretation and avoids common misunderstandings in statistical analysis. Practice, researchers often use a threshold called the significance level to decide whether a p-value is small enough to reject the null hypothesis. The most common threshold is 0.05, but this can vary depending on the field or the specific study. If the p-value is below this threshold, the result is considered statistically significant. However, the choice of threshold is somewhat arbitrary and should be justified based on the context of the research. It's important to distinguish between statistical significance and practical significance. A result can be statistically significant if the p-value is below the chosen threshold, but that doesn't always mean the effect is meaningful in real life. Sometimes, very small differences can be statistically significant if the sample size is large enough. Always consider whether the result matters in the real world, not just whether it passes a statistical test. There are several common misconceptions about p-values. One major misunderstanding is thinking that the p-value tells you the probability that the null hypothesis is true. In reality, the p-value tells you the probability of observing your data, or something more extreme, assuming the null hypothesis is true. It does not provide the probability that either hypothesis is correct. Clearing up these misconceptions is essential for accurate interpretation. P-value can be thought of as a measure of evidence against the null hypothesis. The smaller the p-value, the stronger the evidence against the null. However, it's not a direct measure of the size or importance of an effect. It's simply a tool to help us decide whether our data are surprising under the null hypothesis. Always interpret p-values in the context of the study and other supporting evidence. Sample size plays a big role in p-value interpretation. With a large enough sample, even tiny differences can produce small p-values, making results statistically significant. Conversely, small samples may fail to detect real effects, resulting in large p-values. This is why it's important to consider both the size of the effect and the sample size when interpreting p-values. When researchers conduct many statistical tests, the chance of finding at least one significant result just by chance increases. This is known as the multiple testing problem. It's important to adjust for multiple comparisons to avoid drawing false conclusions from random findings. Methods like the Bonferroni correction are commonly used to address this issue and maintain the integrity of statistical inference. P-values are often reported alongside confidence intervals. While the p-value tells you about the evidence against the null hypothesis, the confidence interval gives you a range of plausible values for the effect size. Together, they provide a fuller picture of the results. Confidence intervals can help you understand both the precision and the practical significance of your findings. In scientific research, p-values are widely used to test hypotheses and draw conclusions from data. They help researchers decide whether their findings are likely due to chance or represent a real effect. However, reliance on p-values alone can be problematic, so it's important to consider the broader context, including study design, data quality, and other statistical measures. Despite their popularity, p-values have limitations. They don't measure the size or importance of an effect, and they can be influenced by sample size and study design. Over-reliance on p-values can lead to misleading conclusions, especially if other important factors are ignored. Always interpret p-values as just one piece of the statistical puzzle. In reporting p-values, it's best to provide the exact value rather than simply stating whether it's above or below a threshold. This gives readers more information and allows for a more nuanced interpretation. Additionally, reporting confidence intervals and effect sizes alongside p-values helps paint a clearer picture of the results. Replication is a cornerstone of scientific research. A single study with a small p-value isn't enough to establish a finding as true. Replicating results in independent studies strengthens the evidence and helps confirm that the observed effect is real and not just a fluke. Always look for replicated findings when evaluating scientific claims. Publication bias occurs when studies with significant p-values are more likely to be published than those with non-significant results. This can distort the scientific literature and give a misleading impression of the evidence. Being aware of publication bias is important when interpreting p-values and the results of scientific studies. Statistical power is the probability of detecting a true effect when it exists. Low power can lead to large p-values even when there is a real effect, while high power increases the chance of finding significant results. Considering statistical power is essential for designing studies and interpreting p-values accurately. Effect size measures how big the difference or relationship is in your data. While p-values tell you about statistical significance, effect sizes tell you about practical importance. Always consider both when interpreting results, as a small p-value with a tiny effect size may not be meaningful in practice. Type I error occurs when we incorrectly reject the null hypothesis when it is actually true. The significance level, often set at 0.05, represents the probability of making a type I error. The p-value helps us control this risk, but it's important to understand that even with a low p-value, there's always a chance of error. Type II error happens when we fail to reject the null hypothesis even though it is false. This is often due to low statistical power or small sample sizes. Understanding both type I and type II errors is essential for interpreting p-values and designing robust studies. In hypothesis testing, you can use one-tailed or two-tailed tests. A one-tailed test looks for an effect in a specific direction, while a two-tailed test considers both directions. The choice affects the calculation and interpretation of the p-value, so it's important to select the right test for your research question. Two-tailed tests are more common in research because they allow for the possibility of an effect in either direction. The p-value in a two-tailed test is typically double that of a one-tailed test for the same data, reflecting the broader range of possible outcomes. Always match your test type to your hypothesis. Statistical tests that produce p-values often rely on certain assumptions, such as normality or equal variances. Violating these assumptions can affect the accuracy of the p-value and lead to incorrect conclusions. Always check the assumptions of your test before interpreting the p-value. Outliers can have a big impact on p-values, sometimes making results appear more or less significant than they really are. It's important to identify and understand outliers in your data before relying on p-values for interpretation. Proper data cleaning and analysis help ensure accurate results. High-quality data is essential for meaningful p-values. Poor data quality, such as missing values or measurement errors, can distort p-values and lead to incorrect conclusions. Always prioritize data quality in your research to ensure your statistical results are trustworthy. A well-designed experiment is key to obtaining meaningful p-values. Factors like randomization, control groups, and blinding help ensure that p-values reflect true effects rather than biases or confounding variables. Good experimental design strengthens the validity of your statistical conclusions. Reproducibility means that other researchers can obtain similar results using the same data and methods. Reporting p-values transparently and providing access to data and code helps ensure that findings are reproducible. This is a key principle of good scientific practice. While p-values are a staple of classical statistics, Bayesian methods offer an alternative approach to hypothesis testing. Bayesian statistics provide probabilities for hypotheses directly, which some researchers find more intuitive. Understanding both approaches can broaden your statistical toolkit. False discovery rate, FDR, is the expected proportion of false positives among all significant results. In studies with many tests, controlling the FDR helps prevent too many false discoveries. Techniques like the Benjamini-Hochberg procedure are used to manage the FDR in large-scale analyses. Most statistical software packages can calculate p-values automatically. However, it's important to understand how these values are computed and what they mean. Relying solely on software output without understanding the underlying principles can lead to misinterpretation and errors. Let's look at some real-world examples. In clinical trials, a p-value less than 0.05 might indicate that a new drug is more effective than a placebo. In social science, a small p-value could suggest a significant difference between groups. These examples show how p-values are used to make decisions across different fields. Policymakers often rely on p-values to inform decisions, such as approving new treatments or implementing public health interventions. It's important that these decisions are based on a comprehensive understanding of the evidence, not just whether a p-value crosses a certain threshold. Meta-analysis combines results from multiple studies to provide a more robust estimate of an effect. P-values from individual studies contribute to the overall analysis, but meta-analysis also considers effect sizes and study quality. This approach helps synthesize evidence and draw stronger conclusions. Open science practices such as sharing data and pre-registering studies help improve the transparency and reliability of p-value interpretation. These practices make it easier for others to verify results and reduce the risk of selective reporting or p-hacking. P-hacking refers to manipulating data or analyses to obtain significant p-values. This can involve trying multiple analyses, selectively reporting results, or stopping data collection once significance is reached. P-hacking undermines the credibility of research and should be avoided through transparent and pre-registered methods. Statistical literacy is the ability to understand and interpret statistical information, including p-values. Improving statistical literacy helps researchers, policymakers, and the public make better decisions based on data. Education and clear communication are key to building this important skill. Clear communication of p-values and statistical results is essential for effective science. Avoid jargon and explain what the p-value means in plain language. This helps ensure that findings are understood and used appropriately by a wide audience. Ethical research practices include honest reporting of p-values and results. Misrepresenting or selectively reporting p-values can mislead others and damage trust in science. Upholding ethical standards is crucial for maintaining the integrity of statistical analysis. Teaching about p-values and their interpretation is an important part of statistics education. Students should learn not just how to calculate p-values, but also how to interpret them in context and understand their limitations. This foundation supports better research and decision-making in the future. Role of p-values in research is evolving. Some journals and organizations are moving away from strict p-value thresholds and encouraging a broader approach to statistical inference. This includes considering effect sizes, confidence intervals, and the overall quality of evidence. The future of statistical analysis is likely to be more nuanced and comprehensive. Despite decades of use, there are still open questions about the best ways to use and interpret p-values. Ongoing research is exploring alternatives and improvements to traditional methods. Staying informed about these developments helps ensure that your statistical practice remains current and effective. P-values are used across many disciplines, from medicine to economics to psychology. Each field may have its own conventions and standards for interpreting p-values. Understanding these differences is important for interdisciplinary research and collaboration. Visualizing p-values and statistical results can make them easier to understand. Graphs, charts, and plots help communicate findings clearly and highlight important patterns in the data. Effective visualization is a powerful tool for interpreting and sharing statistical results. Ultimately, p-values are a tool to support decision-making. Whether in research, policy, or business, interpreting p-values correctly helps ensure that decisions are based on sound evidence. Always combine p-values with other relevant information for the best results. Wrap up: understanding p-values is essential for interpreting statistical results and making informed decisions. Remember that p-values are just one part of the bigger picture. Always consider effect sizes, confidence intervals, study design, and the broader context. By interpreting p-values thoughtfully and responsibly, you can draw more accurate and meaningful conclusions from your data.